Welcome to another podcast. In this episode, we're going to take a look at how to interpret D'Alembert solution, specifically focusing on the effect that the characteristics have for the wave propagation. Now, in order to do this, I'm going to start with just sort of generally talking about the solution, reminding you what D'Alembert solution is. Then we're going to take a look at the characteristics. So let's start with the PDE, which all this is revolving around, and that is, of course, the wave equation. And remember, D'Alembert solution is a solution to a problem having initial conditions, so a solution to the IVP, where specifically u of x0 is f of x, and the initial velocity along the string is given by the function g of x. Together, as we showed in class, these are solved by D'Alembert solution, which is of the following form. And we just want to develop some intuition in this video about what this solution is telling me solutions to the wave equation do, and how they're affected both by position and velocity. So the question that I have at this point revolves around a picture. And so let me go ahead and draw this in. So suppose that I wanted to look at, once again, the xt, or the space-time plane, and I am interested in what's going on at the point x0, t0. So describing it as what is happening at position x0 on the string, t0 time into the future. Well, it turns out that in order to properly describe this, remember this thing moves at speed c, so I want to sort of backtrack here and say, okay, if we go backwards with slope 1 over c, and we go forwards with slope 1 over c, so this would be negative 1 over c for the slope, then those two lines intersect the x-axis. In other words, whatever the initial disturbance was that led to this point, it came from these 2 points. Specifically, if you look at, this is the point x0 minus ct0, and this is the point x0 plus ct0. In other words, the initial point x0, t0 started off x0, 0 down here, and the disturbance spread at speed c, and so backtracking to get to this point had to come from a cone of length, in this case starting from the initial disturbance, spreading out c in either direction. And since this point x0, t0 depends on these initial values here, remember these are characteristic lines, then we know that the solution depends on those characteristics. You can see it right here. This is the line. So you can see here x plus ct, or excuse me, x minus ct. X minus ct equals x0 minus ct0 everywhere along that line. In particular, at the point t equal to 0, which we are on the axis, you get x equals x0 minus ct0. So at the point x equal x0, you get t equals t0. So we know that this line and this line pass through the point x0, t0. These are called the characteristics. This one has slope 1 over c, and this one has slope negative 1 over c. Now, that's not so much the important part as what they're telling us about the solution. Let me just call this point the point A, and we'll call this point the point B. Then I want to ask, what is u of x0, t0? In other words, what is the solution to the wave equation doing at that point? Well, I could just plug x0 and t0 into D'Alembert's equation. And if I did that, what would I see? Well, I would see that u of x0, t0 equals just looking at the first part here, it's f of replacing x with x naught and t with t naught. It's f of x plus c t naught and f of x minus c t naught. But f of x naught minus ct naught and f of x naught plus ct naught is f at a and f at b. So u of x naught t naught is the average of the function f at the points a and b. That seems simple enough, but we've also got to add in what happens with the initial velocity. So that's just this part. That's all we've talked about so far. It's the average of the function f at the points a and b. Easy enough. Okay. Plus 1 over 2c, this would be the integral of x naught minus ct naught, x naught plus ct naught, if we're evaluating at x naught t naught. So where is that interval? Well, if you look, the interval from x naught minus ct naught to x naught plus ct naught is this interval in green. And so what that's telling me is, okay, u of x naught t naught is the average of f at a and b, plus it's the integral over that green line of the function g. And I want to talk about that function g for a second, specifically on that interval. If I was to tell you what is the average value of the function g on the interval from a to b, so we're going back to calculus 2 now, the average value integral is an integral of the form 1 over b minus a, integral from a to b, in this case g of s ds. Now if we replace a and b with what they actually are in terms of x naught and t naught, b minus a turns out to be 2c t naught, and we get x naught minus ct naught and x naught plus ct naught. Well, if you compare this with this solution here, this part of the solution, the integral, the only difference is the t naught factor. And so what this is telling me is u of x naught t naught is the average of f at a and b plus the average of g over the interval from a to b. But it's not quite the same if you've got to multiply it by t naught. So it's this times t naught. Now let's think about that for a second. The average of g is the velocity, right? So we're talking about the average velocity over the interval times time. So what if you do velocity times time? That's displacement. So what you can see here is that this is definitely displacement. It's the average initial displacement of the initial waveform, f of x. And this is also displacement. It's the displacement due to the average velocity initially acting on the wave. And so both of them together are displacements, and so u of x naught t naught is the displacement at this point in space-time. In other words, it's the displacement at the point x naught at some future time t naught, and it depends on what happened at these initial points a and b. And so that is a really, really cool sort of explanation of what's going on here. In particular, if I really wanted to get into it, then we need to look at an example. So I need to just create some room here. Do that by erase all of this right quick. And I erased my little border there. I'll go ahead and put that back in. So I want to look at another example. I want to look at the exact same PDE. So we're going to look at the wave equation once again. Except this time I want to specify my initial conditions a little bit more closely. I want to let the initial position of the wave be a function that hopefully you're familiar with. It's the box function that we talked about in ODE, where this h is the Heaviside function. So this box function is defined as, in this case, it would be 1 for values of x between -1 and 1, and it's 0 elsewhere. So that's the box function. And then the other part of this is I want my initial velocity to be 0. I don't want to have to mess with the initial velocities. It just complicates the intuition that we're trying to develop at this point. So that's the problem that I want to solve. And I want to do that by looking graphically at the following. So based on the conversation that we just had, if we're trying to figure out what's going on with this solution, then what I need to identify is what this initial disturbance causes. And when I say initial disturbance, I mean the fact that on the interval from -1 to 1, the string has height of 1. So imagine it as, I don't know, what's the best way to describe this? Maybe you place a brick of length 2 underneath the string so that it drapes perfectly over the brick, and then you pull the brick out immediately, so sort of instantaneously. And just what would the string do from then on? I mean, that's basically what you're doing here. And what we've discovered is everything has to happen along characteristic lines. Characteristic lines tell me how we're going to interpret this thing. So let me draw some characteristics in. So I am trying to draw lines. So we'll start here. This line has, this is the line with slope +1/c. And then this one is the perpendicular to that. It's got slope -1/c. So try to draw that as close to perpendicular as I can. Okay, so there's those two characteristics. And I want to look at the characteristics in both directions. So I need another set of characteristic lines here that have to be parallel. So these need to be parallel to the others. And I think that's pretty close. Over here we need parallel as well. And so the reason I'm doing this once again is I want to look at what happens in each of these different regions. So I'm going to call this region 1. So everything inside this blue triangle. We're going to call this region 2 over here, region 3 in here, region 4. So 4 is both sides of this, but everything up here in this top part. And let's say region 5 and region 6. And you know, based on the intuition that we just gathered about the solutions to this, let's think about what the solution u is going to be in each of these regions. So I want to talk about u of xt, and I want to talk about its value. So what is its value on each of the regions? So let's make like a little table, if we will. So let's start with region 1. So on region 1, every point in region 1 will depend on lines that are parallel to the blue lines, and so it'll depend on these two initial points. Well, the string at those two initial points, the string has height 1, right? Because it starts off with 1 in here. So let me maybe do a purple for the string. This is the string where it has height 1 right there. So everything inside region 1 has height 1, and so if you take the average of 1 plus 1, you get 2. So u of xt in that case, in region 1, is equal to 2, has the value 2. All right, what about region 2? Region 2, any point in region 2 has characteristics that lie entirely off of the purple line that we start with. So these have value 0. Remember that out here it's 0 to start with, and so the average of 0 is 0. So u of xt is 0 in region 2, and likewise 6 has the same issue. The characteristics over there lie entirely off the starting disturbance. In other words, if you're in region 2 or 6, you don't feel the initial disturbance of the string at all. close to that point. It's further on in time that it'll take to get to your position on the string. And how much time it takes is based on the characteristics. So let's just look at region 3 now. So in region 3, what you notice is so any point in here has the property that part of the characteristic is going to end up on the line, and part of the characteristic ends up off the starting line. So it's the average of 1 plus 0, which ends up being a half. And so that's also true over here in region 5. You can see in region 5, half ends up on the purple line, half ends up off. And so regions 3 and 5 have 1 half. And then if you look at region 4 is outside the small blue triangle, so its characteristics are going to hit on 0 on either side, making it have a value of 0 as well. And so we've completely described what the wave looks like in those regions for all time. So once this wave initially propagates, it's going to start out with a height of 1, and then it's going to almost immediately drop to a height of 1/2. It's just however much time it takes the wave to travel from here to here, right? So it's going to start to peel off and have height 1/2 out in these regions, propagating forward. So I've done a little thing in Maple here to take a look at this, just so you could kind of see it in play. So if we take a look at that, then you can see here that I've entered the Heaviside function. I've looked at the wave speed of 1, and I have also looked at D'Alembert solution. Remember, the initial velocity here is 0, so that's why I don't have plus 1 over 2c times the integral. The integral is just 0 there. So if I define D'Alembert solution in this case, which I have, and I go ahead and plot it, you can see the plot is exactly what we would expect to see. Let me kind of turn this around and get a better view of it. You can see how initially it has height 1, and it stays height 1 inside that triangle that we said, and then once you go outside that triangle, it disperses as waves of height 1/2. You can see the u value over here, height 1/2, forward in time. And the question at this point is, how does the speed affect all of this? Well, the speed here is 1. If I make the speed, let's say 2, so I speed it up and redo everything here, plot it once again, you can see it opened up the wave. Because it's propagating faster, it takes less time to move the disturbance to other parts of the string. It's exactly what you would expect. If I slowed it down, then what you would expect to see is it takes longer to reach parts of the string. So it looks like it's moving faster, but it's really not, because remember x, the axis down here is the position of the string. So it takes longer to reach further out along the x-axis to actually disturb things, because the speed is slower. But the initial characteristics of the wave remain exactly the same. It has a height of 1, and then as the string moves forward in time, it drops to having a height of 2.